Hey everyone, and welcome to The Explainer. Today, we're jumping right under the hood of modern industry to check out the thermodynamic heartbeat of massive global machinery, the diesel cycle. We see the results of this cycle literally every single day, right? It's moving our goods, it's powering our infrastructure, but understanding the precise physics of how it actually works is a really incredible journey. So let's get into it. We've got a clear roadmap for today. We're going to start with the sparkless engine, break down the 4 steps of the cycle, and then get into calculating thermal efficiency. After that, we'll compare the diesel to the Otto cycle and wrap it all up with some massive real-world applications.
Section 1. The sparkless engine.
Okay, I want to kick things off by challenging what you might already know about internal combustion. Think about it. How exactly do engines ignite fuel without a spark plug? Most of us are super used to the standard 4-stroke petrol engine in our cars, right? The one that absolutely relies on a spark to ignite a fuel-air mixture. But the cycle we're analyzing today, it operates on a completely different set of rules.
Let's define the core mechanism here. The diesel cycle is a combustion process where fuel is ignited solely by the intense heat generated during the extreme compression of air. So air is drawn into a combustion chamber and squeezed so incredibly tight that it becomes scorching hot. Only then is the fuel injected into that ultra-hot environment, causing it to spontaneously ignite. The whole shebang happens entirely without the use of a spark plug. No spark, just pure pressure and heat.
Moving on to Section 2, 4 steps of the cycle.
Let's meticulously walk through this idealized mathematical model step by step. It reveals 4 distinct phases. Step 1 is the isentropic compression of the fluid. This is where heavy work is being done by the piston compressing the air, without losing heat to the outside. Boom. Step 2, constant pressure heating. This is where the intense combustion of the fuel actually happens. Step 3 brings us to the isentropic expansion, where that superheated working fluid rapidly expands and pushes the piston down to produce all that usable work. And finally, step 4 is constant volume cooling, where the exhaust is simply vented right out.
This brilliantly illustrates the ultimate balancing act of the entire cycle. On one side, you have the energy transferred into the system. That's the work put in by the piston compressing the air, plus the heat added by the fuel combusting. On the flip side, you have the energy flowing out, the gross work done by the fluid expanding and pushing the piston, alongside the heat that simply vents away.
So what does this all mean? Well, ultimately, the net work produced by this engine is quite simply the difference between the heat added to the system and the heat rejected from it. That network, which is usually represented by the area enclosed inside those 4 steps on a PV diagram, is the useful energy that actually propels a vehicle forward or generates electricity.
Section 3. Calculating thermal efficiency.
Now, the specific formula for maximum thermal efficiency under cold air standard analysis is pretty dense with Greek symbols, so let's gently decode them with a quick cheat sheet. These are the key variables that dictate exactly why the cycle behaves the way it does. We have eta for thermal efficiency. Then there's alpha, which represents the cutoff ratio. That's the ratio between the end and start volume for the combustion phase. Next up is R, representing the compression ratio. And finally, gamma, which is the ratio of specific heats. What's really fascinating here is how the cutoff ratio, or alpha, isn't just about volume. It mathematically links directly to real-world temperatures. When you break it down, alpha is tied to the inlet air temperature and the actual physical flame temperature of the fuel used. More specifically, it relates to the adiabatic flame temperature based on your precise air-to-fuel ratio. It's a brilliant connection between abstract volume and intense physical heat.
But, we always have to ground this theory in reality. These equations, they only give us the idealized maximum efficiency. When you build a physical, real-world engine, the actual thermal efficiency is always going to be significantly lower, simply because real machines suffer from physical friction and heat loss to their surrounding environment.
Section 4, Diesel versus Otto cycle.
Which brings us to a really fascinating paradox. If you mathematically lock in a set compression ratio, the ideal Otto cycle, the one you'd find in your standard gas car, is actually more efficient on paper. But the diesel engine completely dominates the real world. Why? Well, if a petrol engine tried to run at the massive compression ratios a diesel engine uses, you'd get catastrophic self-ignition, engine knocking. The diesel cycle thrives precisely because self-ignition is the entire goal. It allows the engine to safely operate at vastly higher and therefore far more efficient compression ratios.
It's also definitely worth noting that the mathematical formula for diesel efficiency is more complex than the Otto cycle. And the reason for that is pretty straightforward. In the diesel cycle, heat is added at a constant pressure and rejected at a constant volume. The Otto cycle, by comparison, handles both the addition and rejection of heat at a constant volume.
We do have to clarify, though, that these are just models. While the idealized diesel cycle assumes a perfectly constant pressure during the initial part of combustion, real physical diesels actually do experience a slight pressure bump during this period. The sharp distinction between the cycles definitely blurs a bit once metal actually meets the road.
All right, Section 5, Real-World Applications.
Just consider this incredible number for a second. 0.26 pounds per horsepower hour, or if you prefer, roughly 0.16 kilograms per kilowatt hour. That represents the extremely low specific fuel consumption achieved by very large marine diesel engines. Outside of combined cycle power plants, which remember use two engines, diesel engines had the absolute lowest specific fuel consumption of any single-cycle large internal combustion engine out there.
Because of that incredible efficiency and the overall low-stress nature of the cycle, these engines boast uniquely long lifespans and significantly lower operational costs. That makes the diesel cycle the undisputed king of massive machinery. It is literally the powerhouse behind large trucks in North America, heavy-haul railroads, diesel-electric locomotives, earth-moving equipment, massive surface ships, submarines, and global power generation. It is everywhere.
But hey, it doesn't just power massive ships and trains. Get this, the exact same sparkless principles are used to fly tiny, simple model airplanes. While they do rely on special fuels, these variable compression model engines operate without spark plugs, mimicking the exact same thermodynamic cycle as the giants of industry.
The origins of all this power actually stretch back a lot further than you might think. It was the 19th century research of Nicolas Leonard Sadi Carnot, who was originally studying experimental engines with external flames, that established the thermodynamic value of compression. Carnot's work laid the foundational physics for this long before the first modern diesel engine was ever even assembled.
And this historical thread leaves us with a truly fascinating implication. Because the diesel cycle relies purely on mechanical compression for ignition rather than an electrical spark, the diesel engine theoretically could have been invented entirely without the aid of electricity. Which brings us to a provocative question to end our explainer today. If Carnot proved the value of extreme compression so early on, what other modern technological marvels could theoretically exist entirely off the electrical grid? It is definitely something to think about the next time you see a massive locomotive rolling by. Thanks so much for joining me for this deep dive into the diesel cycle.